on the screen. Here you have a new hyperbolic function, hyperbolic tangent. So as for as for trigonometric functions, it is defined as sinus hyperbolic by cosinus hyperbolic. So if you make use of the definition of sinus and cosinus, you will see that it will be e to the power x minus e to the power minus x over e to the power x plus e to the power minus x. So we want to show this limit, to prove this limit. Then we make use of this formula for hyperbolic tangent of x. It will be sinus over cosinus. First of all, we know that due to the definition of cosinus, it will be e to the power x plus e to the power minus x. So the numerator here goes to 2 as x goes to 0. Agree?
Yes, I agree.
So the limit will be 1. So as for this cosinus, if hyperbolic cosinus, we have no problem. So we have only sinus, hyperbolic sinus of x over x. But we know this limit from the previous exercise. So we have that our desired limit tan x over x will be 1 over cosinus multiplied by hyperbolic sinus of x over x. From the previous exercise, the second limit is 1, so our limit hyperbolic tan of x over x will be 1. This means, to see a remark, that if x goes to 0, the equivalent function for the hyperbolic tangent of x is x. That is, the behavior of this function as x goes to 0 is similar to the behavior of the function x as x goes to 0. Is it clear?
Yes, it's clear.
Good. So now we take another exercise. It will be really something from the second remarkable limit. That is, we want to find the limit as x goes to infinity of x plus 2 over x plus 1 to the power x. So first of all, you see, we rewrite our function in the brackets in the following way. So the numerator we write as x plus 1 plus 1. Then our fraction x plus 2 over x plus 1 will be 1 plus 1 over x plus 1. As usually, we want to have a power of the same type as here, as in the second term. 1 plus something. And the power have to be something. So if 1 over something goes to 0, then we have the power of this something. Is it clear, or I have to explain more clearly? Eric?
No, for me it's clear. But I'm not sure about anybody else that maybe needs a little bit more explanation.
Mikhail, is it clear?
Yes, it's clear.
Valentina, is it clear?
Yes, it's clear.
Onya, clear? It's clear.
Oui, c'est clair.
So you see, now, I want to have something in the power of this bracket, something like x plus 1 as x goes to infinity. So I rewrite the power x as a fraction, x multiplied by x plus 1 divided by x plus 1. Then, you see, I rewrite my limit as 1 plus 1 over x plus 1 to the power x plus 1, and in the square brackets, I have the power x over x plus 1. So, first of all, here, in the square brackets, we know that this limit will be e. Yes? If you do not like x plus 1 as a variable, you can change x plus 1 by t. X goes to infinity, t goes to infinity. Same thing. Agree?
Yes, agree.
So, as this limit is e, we have to find the limit of e to the power x over x plus 1. So, once more, I recall you that in this case, we make use of the continuity of our exponential function. I write this fact here. So in fact, you see the limit of e to the power to something to the power x over x plus 1 will be exactly the exponential function of the limit and this limit x over x plus 1 as x goes to infinity is 1. So the desired limit is e. Is it clear?
Yes, it makes sense. Everything's clear.
Yes, it's clear.
Good. Thank you. So now, the next example, the next exercise. You see here we have some limit 1 plus 1 over x squared as x goes to infinity. Then, as in the previous case, you see, I want to have for my bracket here, I want to have a power x squared in order to use the second remarkable limit. So I rewrite my limit in the following way. So 1 plus 1 over x squared to the power x squared, and all these to the power 1 over x. So as in the previous case, we have to find, excuse me, the limit as x goes to infinity of e to the power 1 over x. Then it will be the exponential function of the limit, and this limit finally will be 1. Agree?
Yes, I agree.
And our other colleagues, they agree?
Yes, agree. Yes, agree.
Good. Mikhail?
Yes, agree.
Yes, I agree.
Okay. So now, for you, we have, if you want, some results which follow from the continuity of the corresponding function. So maybe it was better to formulate this lemma before our exercises, but I think I've explained you our problems, but here you can read once more some properties of the function a to the power x log of x, and what will be necessary for our next exercises. You see, I want to find a special limit. If I take two functions, u of x and v of x, and I want to find the limit as x goes to 0, x0, excuse me, u of x to the power v of x, and I know that the limit of my function u of x, which is supposed to be strictly positive, is a, and the limit as x goes to x0 of the second function v of x is b, then the whole limit is a to the power b. So you have to believe me only, or maybe you know this from your lectures. But what is important, we will use this result. We will use this result in a special case when the limit of the function u of x as x goes to x0 is 1, and the limit of the second function v of x as x goes to x0 is infinite. So in this case, you see, if I want to find the limit of u to the power v, it will be the exponential function of the limit x goes to x0 of u minus 1 multiplied by v. So in this case, we have an indeterminate form like 1 to the power infinity. You see? And we will use this corollary in the next exercise. For example, you see, I want to find the limit as x goes to infinity x squared plus 1, x squared over x squared minus 2 to the power x squared. So, in the framework of this corollary, you see my function u of x is x squared plus 1 over x squared minus 2. And my function v is exactly x squared. So, you see, if we want to use this formula 3.19, I have to find the limit as x goes to x0 of the product u minus 1 times v. Okay, so I write this product u minus 1 times v will be x squared plus 1 over x squared minus 2 minus 1 multiplied by x squared. And this gives that this product will be 3x squared over x squared minus 2. Agree?
Yes, I agree.
No problems, I think. So, our desired limit, our initial limit is the exponential function of limit as x goes to infinity of this 3x squared over x squared minus 2. I hope here you have no problems, and the limit is 3, then the desired limit will be e to the power 3, e cubed. I agree. You agree?
Yes, I agree.
Agree? Mikhail?
Yes.
Good.
Yes, sir.
So now, you see another limit, in this case, as x goes to 0, as x goes to 0 of 1 plus x squared to the power cotangent square of x. So, as in this corollary, or as in the previous example, we have, first of all, u is 1 plus x squared, that is, u minus 1 is x squared, and v is cotangent square of x. So, you see, in order to find our limit, our desired limit, we have to calculate the exponential function of limit x goes to 0 of this product, u minus 1 and v. Then, you see, it will be the limit as x goes to 0, x squared over tangent square of x. Then, knowing the definition of our function tangent square of x, we rewrite the argument of our exponential function in the following way. And knowing the first remarkable limit here we have 1, and here, as for the cosine square of x, as x goes to 0, we have also 1, that is the answer will be e. Is it clear?
Yes, it's clear.
So now, let us, we have time. So what I propose, I will send you some exercise. We will try to do it. You will try to do this exercise, for example, in 10 minutes. If you have the ideas, or it is better to have the answer, you will send me a picture by your telephone. And if you will have some problems, then either I will send you the solution, or we can discuss this on the screen. Agree?
Okay.
Okay.
Okay. So now it's finished as for this file, the seminar. So I will try to send you. I will try to send you the file. It will be this one. If you do not see this file, I can open this file here and where is it? Here it is. So so can you see the formulation of our problem?
Yes.
So you see, we had something similar to this problem, and you can try to use your files from the previous seminar in order to find the solution, to find this limit. So you have some minutes to solve this exercise. Okay? Try to do this. Is it clear, the formulation?
Yeah, everything's clear.
So, during our, it seems to me, last seminar, we had a similar exercise. So you can use your notes or our files in order to have an idea. You see, the hint is we have to change the variables in this case. So 10 minutes, and then we will discuss how to do this. Okay?
Okay.
Okay, got it.
So I am waiting. So the ideas, Eric, what do you think about?
Well, I think that we'll need to break down to different relations. For example, x would equal to the n square root of x.
No. Eric, you see here, and for all the people, as in the previous exercise, it was x to the power, I don't know, m minus 1 and over x to the power n minus 1. Here, in this exercise, we take a change of variables. X is 1 plus t to the power 1. It was x to the power n, not the nth root, but x to the power n or minus 1. You see? So the idea was to replace x by 1 plus t. If x goes to 1, 1 plus t, then t goes to 0. Okay?
Yeah, I understand that.
So you try to find a corresponding change of variables. In this case, it is something similar, but it is not exactly the same change of variables. The change is good, but we need a power to this 1 plus t. You see, something like this. So, in fact, another hint here. We want to use the binomial theorem. You see? So, after your change of variables in the numerator and in the denominator, you have something like 1 plus t to a power which is a natural number. Is it clear? So try to find this change of variables. So the ideas, Eric.
So we know that this same thing equals to k over n, correct?
It will be k over n. I'm agree. But how you obtain this result? Can you show me?
It's like we need to change the variable, so I need to put in the place of x is equal 1 plus t, and you need to
N plus t to the power, Valentina, to the power, to what power?
for the moment I think in the variables is 1 plus t on the power 1 over n.
No. To the power, Valentina, try to define your x as 1 plus t to the power n times k. What do we have?
Oh yeah. Okay. So you have in the numerator do you have 1 plus t on the power k?
Yes.
Yes, and in minus 1, and
Yes.
in the denominator is 1 plus t power n. So we can simplify in this mode, that is k over yes, over n.
So you see, Valentina, you have to use the binomial theorem in order to open the brackets if you want. 1 plus t to the power k will be a sum of k terms minus 1, so 1 disappears in the numerator, in the denominator, and then you will have in the numerator k multiplied by t plus so on plus t to the power k, and in the denominator, excuse me, you have nt plus so on plus t to the power n, and t in this case goes to 0.
0, that t tends to 0, yeah?
So in this case, the limit will be k over n. So I will show you the solution. Eric, are you agree?
Yes, I understand it now.
Michael. Michael. Onya. Tiens,
Yes.
Onya. Est-ce que tu comprends comment faire?
Je pense que oui, mais j'ai pas trop compris en fait par rapport au n racine de x, c'est pas x puissance 1 sur n.
Tu vois, Onya, dans ce cas-là, je vais montrer la solution tout de suite, mais si tu prends x est 1 en place t puissance n k,
Mhm.
Tu vois, après, tu vois x puissance 1 sur n,
Mhm.
tu auras tout simplement 1 plus x puissance k.
Ah. Mhm.
Tu vois? Et
Oui.
donc, après le théorème de binôme,
Mhm.
tu peux appliquer ce théorème et puis, bon, donc, ce machin dans, ça va disparaître.
Oui.
Donc, tu auras tout simplement k multiplié par t. Tu vois, je mélange de langues.
Mhm.
Alors, je vais montrer la solution et on va discuter tout le monde. D'accord?
D'accord.
Et c'est là. So, for all the people, you see, I take x as 1 plus t to the power nk. Then, if x goes to 1, my variable t goes to 0. Agree?
Yes, I agree.
Yes.
Alors, then, you see the nth root of x will be 1 plus t to the power k, and the kth root of x will be 1 plus t to the power n. Agree?
Yes.
Then, the binomial theorem. In the numerator, you will have something like this. So, no 1, because here we have something like -1. Okay? And in the denominator, we also have something -1. So no 1. All the terms at least are of order t. And t goes to 0. So we can simplify our fraction by dividing by t, and we will have that this limit will be k over n. Is it clear?
Yes, it's
Yes.
clear.
Yes.
D'accord. So the next exercise. The next exercise will be as follows. Next. You see, it is an exercise where we have to use the first remarkable limit. So in this case, also, we have to make use of the change of variables. You see here, as x goes to pi, then the numerator of our fraction is 0, and the denominator is always goes to 0 as x goes to pi. The idea is to use some simple change of variables. So you you try to do this, you have 10 minutes, and then we will discuss. Clear?
Yes.
Yeah. On attend. the ideas.
We need to assign another variable. Is like whatever variable, white, for example, and this is p on the power 2.
No, Valentina. You see, you have x goes to pi. If I take a new variable pi, for example, yes, which is pi minus x, what do we have?
Can you repeat? Excuse me.
You take a new variable y, which is defined as pi minus x. What do we have? You see, what pi square minus x square. It's pi minus x pi plus x. Yes?
Yes.
If you take your variable y, which is pi minus x, then y goes to what as x goes to pi? Eric, Onya,
Yes.
you, Eric, do you understand what can do? Maybe you have enough already.
I'm sorry, Professor, but I can't really understand you. There seems to be like some sort of static in the question.
So, Eric, as x goes to pi, if I take a new variable y comes like pi minus x, you see, then y goes to what as x goes to pi?
No, I'm sorry, Professor, but I can't hear you for some reason.
Here,
Excuse me. Alexis,
I think that is my internet, but I talk with Eric, and Eric is the same. I can't listen very well.
now, problem with connection. As for me, I have no problem. Maybe, where are you now? In Dolgoprudny?
Yes.
Yes.
Okay. So, as this exercise, we will show you the solution and third exercise. It will you agree?
Yes.
So I will show you, we will discuss. Okay. So the solution. You see, if I have, if I change my variable in this sense, in this way, so take a new variable, y is y minus x, and you will have that x is I minus y. Yes. That if x goes to pi, y goes to 0. Agree?
Yes, I agree.
So the denominator of our fraction is pi minus x times pi plus x. Agree? Y squared minus x squared. Problem of correction. Now, you can
Not clear. I don't understand your words. It's like that
okay.
sounds very good.
Can you see the picture, the file on the screen?
No, I cannot.
I can't too. It's black. I don't know.
It's black. Oh,
Yeah.
so this is a problem of connection. It's not my mistake. I'll send you the file with the solution and also file with the new task. Can you hear me now?
Yes.
So I send you the file with the solution to this exercise. The file with something like home task, and we can discuss this third exercise next Friday. Agree?
Yes, agree.
Well,
Okay, Professor, yeah.
Eric, can you hear me?
I hear you, but not that well.
So I think I send you the solution and also third exercise as a home task. Okay?
Okay, understood.
So, see you on Friday, next Friday. Thank you very much.
See you, teacher. Thank
you.
you.
Okay, thank you,
Ciao.
Professor.
Thank you so
Ciao, ciao.
much.